Okay, students, for Survey of Calculus, we are going to look at some review problems for our test coming up. So the first thing that I'm going to begin to go through here a little bit is, okay, if you have a given graph, well, you want to know all the different things about it, like the concavity, the points of inflection, where the function's increasing and decreasing, and that kind of thing. So you want to be sure that you can write your intervals real well. So first thing we're going to look at is, where is this graph concave up? Well, you got to identify the points of inflection. On this particular graph, I tried to make the points of inflection pretty easy to see. I mean, they're put on the graph, so that would be one place where your concavity is, you're doing concave up. Another piece would be this right here. And remember, concave up can kind of look three different ways. It can be that full U shape like that, or it could be half of that, more like that, which kind of like is what that is. So you would name those intervals as open intervals right there. So concave up, we're going to say from negative 1.4, and then that ends at 0. See, we're naming these with x values. And then union, then it starts at positive 1.4. And then it goes on forever, so that would be where you're concave up. Okay, so the other thing that I want to kind of look at here is, with this particular problem, the next statement is, where is the second derivative negative? So a couple of things I want to remind you of. Concave up, I gave you this little visual. If you do the second derivative, happy guy means concave up. Okay, well, if you do the second derivative and you got sad guy, this dude here is sad, so that would be concave down. So really, this problem right here is the same thing as, where is this concave down? Okay, so what I'm going to do is just highlight this on here. So that would be one place where you're concave down, and this would be the other place where you're concave down. And remember, concave down has shapes just going the full downward kind of U shape, or half of that. It's important that you understand that there's different ways concave up and concave down could be. Then again, what we'll do is we'll name this in interval notation. Okay, so this is going to go from negative infinity until we get to the point of inflection where the concavity changes at negative 1.4, and then union, it will be from 0 to 1.4, like this then. Okay, and that would be the answer to the first two questions. Okay, just a different way of asking that. Now the points of inflection are going to be all of the places where the concavity changed. So I'm going to highlight these 3 points of inflection. That would be where the concavity changes. If I'm asking for a point of inflection, then I want an actual point on the graph. So we'll say negative 1.4. I think that is 39.6. These little symbols there are approximate symbols. So I'm just going to put that. And then we have 0, 0 is another point of inflection. And then 1.4 and negative 39.6 is a third point of inflection. Okay? Okay, so I'm going to kind of pause here. Now that takes care of the concavity. Now what I'm going to do is just erase this stuff that I did on my graph, including the concavity, because now we're going to start talking about increasing and decreasing. Okay, so increasing, first of all, this question right here is saying, where is the first derivative positive? And remember, if the first derivative is positive, that means the function's increasing. Okay, so I'm going to identify regions from left to right where the function's increasing. So from here to here, and then right there, of course, you have a local max. Okay, another place where you would be increasing would be from this local min to infinity. So that right there would be a local min, like that. All right, and that's it. Every other place is decreasing, so I'm just going to name this in interval notation. So the first one that I highlighted is from negative infinity until you get to that local max, which looks like 2. And then the next place is going to be what looks like, that would be negative 2, I'm sorry. And then from here, this looks like from 2 and beyond. So that would be where the function is increasing. Okay? Right? The next problem is decreasing, and the key thing that you want to remember is if the first derivative is negative, that just means the slope of the tangent line is sloping downward, so the function's decreasing. So what we'll have here is from this point to here, we're decreasing. Now what happens there, we're going to exclude that point right there. So the idea right here is right here, the derivative is equal to 0, so that will not count for decreasing. The derivative has to be strictly negative in order for it to be decreasing. So I'm going to break this up into 2 intervals. We're going to go from -2 to 0, and then we're going to go from 0 to 2, and then that will answer the question of where this function is decreasing. Okay? All right, that'll wrap that up then. Okay, and then we have just one other thing on here. Give the x values where is f of x 0? And this is saying where is f of x 0. I have a sneaking suspicion that I intended to type out where is f prime of x equal to 0. So I'm going to do that. Now I'm going to basically just erase all this stuff on here. So the places, the derivative is 0 wherever you have a horizontal tangent line. So there's 3 places. So you don't necessarily have to be at a min or a max, because this point right here is neither a min nor a max. Okay, so the idea with this is it looks like there are 3 places where you have a horizontal tangent line. -2, 0, and 2 would be those x values. I think pretty sure that's what I intended on that. And that's the only places where you have a horizontal tangent line. Okay, so that's the first problem. You can pause the video here if you want to and need to write down or think about this. Always good to just do these on your own. I'm just trying to explain and refresh your memory on what these things mean. So I'll move down to the next problem here. So this problem, we have lots of things to consider here, like for instance, you have these open circles there, so the function, although it's defined there, it's not defined at that particular point. Okay, you kind of have what we call a removable discontinuity, so the places I'm highlighting in green, those are where the function is defined. Okay, so what we're looking at is first of all, the absolute maximum. All that means is what is the highest value of y. Okay, so the highest value of y that you're ever going to hit is going to be right here. Okay, so what we usually say is this y value, I'm asking for the x value, so it looks like, and I didn't write all these out, but this is just the graphs going 2, 3, 4, 5, 6 like that. Okay, so it looks like that that absolute max, that's an absolute max, is going to occur at x equals 4. Okay. Right, next thing is asking for where is the absolute min. Okay, so the absolute minimum is going to be the lowest point. So if you look at this, I didn't see this originally, but problem is you have a bubble there. So you have an open interval, and since that's an open interval, the y value, you could never pinpoint it to something precise. Okay, it's just going to get close to -1. Okay, that's the y value right there. I think that's 1. I'm sorry, to +1. So it's never going to make it to +1. It's just going to become like 1.0000 as close as we want to 1, but it'll never hit that. So if you have a bubble, that cannot be an absolute max or min. Okay, so in this case, we do not have one. Okay, all right. So that's what that means. So absolute max is the absolute highest y value. Absolute min is the absolute lowest y value. Okay. Now I'm going to erase this now. I'm going to talk about what a relative max is. So basically a relative max, the graph has to look like this. Okay. The function has to increase, hit the place where the derivative is 0, and then it's got to decrease. So we got to identify any of those places that happen like that. Okay, so let's look at the relative max. Okay, one place where the function increases hits a high point, a defined high point, and decreases is right there. Okay, so that would be at 1, 2, 3, that would be at 4. And that's the only place where I see that happen. So that would be at x equals 4. Okay. Now, a relative min is just the opposite. Okay, that would mean the graph does this. Okay, it decreases, hits a low point, and it has to be defined where that's a place where the tangent line would be horizontal. Then it's got to increase. Okay, so I see this happening two places. I see this happening here, and I see it happening there. Okay, so these two things that I'm checking off, which would be at 2 and 5, would be your relative minimums. That's the only places on the graph where I see the graph changing from decreasing to increasing. It's okay that that's a sharp point. That doesn't make any difference. It's still a min. Okay, that doesn't matter. Now, one thing I wanted to point out on this point right here is not a max because it's not a defined point. Okay, so that's why I did not include that in part C of the answer. Okay, so that should wrap us up on page 1. So I'm going to pause for a second, then we'll move on to page 2. Okay, so as I move to page 3, now we're going to look at the kind of typical thing we learned. You're given a function. You want to find critical values. You want to find where the function's increasing, decreasing, where you have relative min and max, using calculus methods. And of course, you can graph this on a calculator and verify your answers. So the thing that you want to make sure to remember is a critical number. You got to look for two things. Okay, 1, where is the first derivative equal to 0? 2, where is the first derivative undefined, if it is undefined. Sometimes it is, sometimes it isn't. So the way you start with a critical number is you go ahead and you do your first derivative. So on here you would have negative 6x squared plus 6x plus 120. Okay, that's your first derivative. That's simple power rule. Second thing you want to do is this thing is never undefined. Okay, so that first derivative right there, x can be anything. There's no zero denominator or anything like that. So we move on to where is this derivative equal to 0? So what I'm going to do is set this first derivative equal to 0. Okay, now this is a quadratic equation. You want to try to solve this by factoring. A good way to start is to divide by or just take out the common factor of negative 6. Okay, so I'm going to take that out. You could also just take a 6 out. I generally recommend if the number in front of the highest power is negative that you take it out. So I'm going to have negative 6. I'm just going to kind of multiply backwards. Negative 6 times x squared would give you the negative 6x squared. Negative 6 times minus 1x would give the 6x. And then if you take 120 divided by 6 on that, that gives you 20. So what I would have here is minus 20. Okay. Okay, so now we can continue to factor this a little bit further. Okay, so I've just taken that out. Now one thing that you can do on this if you want to is you can divide both sides by negative 6. So what you would end up getting then is x squared minus x minus 20 equals 0. And this is a trinomial that factors. So when you factor this, okay, the first term is going to be the x squared. So that's going to be, of course, x times x. The last term is going to be the 20, and you're finding numbers that multiply to give 20, like 1 and 20, 2 and 10, 4 and 5. 4 and 5 is the right choice, and the reason why it's the right choice is because when you FOIL and do this inner term, you would get 4x, and this outer term would be 5x, and you want that to add up to negative 1x, and the way to make that happen is to have a positive 4 and a minus 5. So your signs are going to go like that, okay? So what you end up having now is you've got it factored, so now you just let x plus 4 equal 0, let x minus 5 equal 0. You can solve those two equations in your head, and then those would be your critical numbers. So we just say x equals negative 4, and x equals 5 would be the critical number. So those are going to be two places on this original graph where the tangent line's horizontal. Okay, so that's how you want to do a critical number. Factoring is a key thing. You could also do the quadratic formula on that too if you wanted to, but it's more work and more time consuming. Okay, now what we want to do is we want to get into the sign chart. So when you do a sign chart, you generally want to just draw a number line, and you want to identify your critical number. So we have a critical number at x equals -4. We have another critical number at x equals 5. Okay, so it's going to go like this. All right, and these are the two places where the first derivative is 0. All right, then what we typically do is we do test points. Okay, and my derivative, I'm going to write my derivative. The best place to plug it in is just the factored form. The -6 doesn't have any impact on that. So you can use x plus 4 times x minus 5 to test the function, or you could even go all the way back here if you wanted to. Okay, just find it easier to go here because removing that -6 makes no difference on this sign chart. Okay, so what I'm going to do is plug in. I'm going to pick a test point to the left of -4. Let's go with -5. So that would be -5 plus 4 times -5 minus 5. That is a negative times a negative. That's a positive, which means the function is going to increase. Okay, pick a test point between -4 and 5. Let's go with 0. Plug into the factored form of that derivative. We'd have 0. Whoops. We're going to have 0 plus 4 times 0 minus 5. So that's a positive times a negative, which is a negative. That means the function is decreasing on that interval. And finally, I'll pick a test point bigger than 5, like a 6. Plug into the first derivative. I'm going to have 6 plus 4, 6 minus 5. That's a positive times a positive, which is a positive. That means the function increases. Okay, so the sign chart answers the rest of these questions for you. So basically what we found is we increase here and here. So we write that in interval notation. So that will be -infinity to -4. Again, use your critical numbers, not those test values. And then 5 to infinity. So that's where you're increasing. Okay, decreasing is between -4 and 5. So we write that like that. That's where the function is decreasing. And then as far as figuring out the relative max and min, well, what I usually do on this is just kind of look at my sign chart, and I just kind of sketch out how this graph's going to go. The graph's going to increase. It's going to hit a high point where the derivative is 0. It's going to start decreasing, hit a low point, and go like that. Okay, so that means this is your max. This is your min. Okay, and then we're going to name those points. So the max is going to occur at -4. We'll have to figure out the y value. The minimum is going to occur at 5, so we'll figure out the y value. Now, generally what I would tell students to do on this is you're either going to plug into the function, so you could get these answers this way. Your function that we are analyzing is -2x to the third plus 3x squared plus 120x. So you can work out f of -4 just by plugging in, and you can work out f of 5 by plugging in. So you could do -2 times -4 to the third plus 3 times -4 squared plus 120 times -4, and then do the same thing with 5. You would do -2 times 5 to the third plus 3 times 5 to the second plus 120 times 5. Now, you're going to use your calculator on that. And if you want to, I think a good way to use technology to do this problem anyway is just to close off by going through and graphing the function that we're working on. So we're working on the function -2x to the third plus 3x to the second. Oh, crap, nah, I'll do that all the time. Start again, -2x to the third. You have to do your down arrow to get back to where you want. Then plus 3x squared and then plus 120x. And probably what I would do on this is I would just start with a standard window. That's which one I need to put the x in there. Okay, I'd just go zoom 6, standard window. You probably need to expand the y values. Okay, so I'm going to go ahead and just take the y's down a little bit. I don't know what, I'm just going to do something like negative 100 to 100 by a scale of 10, and then we'll try to regraph that. Okay, that looks a little better. We probably could go a little bit further, so I'm going to do like, let's just be brave and go negative 300 to 300. I just want you to see the entire graph. That's why I'm taking the time to do that. So let's try the window like that. Okay, I'll graph it. Okay, and that starts looking better. Okay, I think I'm going to do one more time, and I think I'll have it here. So I'm just going to go negative 400 and then to 400 just because it'll look better. Okay, and sometimes, oh crap, what did I put in? 4. 400 like that. There we go. That's what I wanted to do. Okay. All right. Now that looks good. Okay. Now what I'm saying that you can do is you can trace these two values like this if you want to. So negative 4, you can just type trace negative 4, and then that'll give you negative 304. Okay. So you can just do it that way, save a little bit more time. And to me, you're checking your answer as you do it this way too. Trace at 5. Then you have 425 is where that maximum is then, okay? All right, I probably should have taken this thing all the way out to negative 500, and then you would see that max a little bit better, so I am going to do that, okay? And there you go, that's what it looks like, okay? So you've got your min at negative 4, negative 304, you have your max at 5, 425. And you can tell that our sign chart matches up with this, so therefore that has to be a correct answer. Okay? Okay, so I'm going to move down to the next problem. The next problem is the technique of taking a function and using calculus methods to determine the absolute minimum and absolute max. On a problem like this, since you're in a calculus class, I want you to use calculus methods to find that. But obviously, in the modern world, you want to graph it on your calculator. You want to verify that you're right. So what this problem is talking about is here's your function. This is a cubic function, and you're given a closed interval. So we have this intermediate value theorem that we talked about. If you have a continuous function and a closed interval, then there's guaranteed to be an absolute max and an absolute min somewhere in that interval. Okay, and it could be, more than one absolute min and more than one absolute max because they could have the same value. So the methodology that we learned to do on this, the very first thing that you want to do is you really want to find critical numbers. So we want to start by doing the first derivative, and that's going to be 6x squared minus 6x minus 12. Okay, that's always defined. Okay, this is a continuous function. The derivative is continuous. It's always defined. So set it equal to 0. Okay, and you want to try to solve this by factoring. Most of these problems are designed so you can factor. This has a common factor of 6. So I'm going to go ahead and remove that common factor. Okay, like this. Okay, then I'm going to go ahead and factor that a little further. Okay, that looks a lot like a problem we did earlier. Okay, we take the 6 out, and then again, the first part of your FOIL would be the x squared. So your first term is just going to be x and x. Your last term on the FOIL is 2. So there's only one way to do that. 2 times 1 or backwards won't make any difference. So I'm just going to go 1 times 2 to get 2. Okay. Then the key thing is I usually tell students to figure out your signs at the end. When you FOIL this, that inner term is 1x. This outer term is 2x. You're hoping this turns out to be negative 1xc. Okay, if you just take the time to write that down, I mean, it makes it pretty clear. The only way to make 1 and 2 add up to negative 1 is to have a positive 1 and a negative 2. So the 1's positive, the 2's negative. Okay, like that. Okay, now if you wanted to, you can just ignore the 6 if you want to, or you can divide by it, like that's what I'd do. So you would just end up having x plus, you just could do this in your head now if you want to. So you have x plus 1 equals 0, so one of your critical numbers is at -1. And then you would have x minus 2 equals 0, so you have another critical number at x equals 2. So step 1 is getting the critical numbers. Okay, step 2, what you want to do, and you don't have to do a sign chart to do an absolute min or max on an interval. You just need to do this. You need to take the endpoints. Okay, so we're going to evaluate these endpoints in this function. Okay, so I'm just going to go like this. I'm going to go 2 times -2 to the third minus 3 times -2 to the second minus 12 times -2 plus 24. So we got to do the endpoints. We also got to do the 4. So we're going to do g of 4. Okay, so we do the same thing, just plug in 4. 2 times 4 to the third minus 3 times 4 to the second minus 12 times 4 plus 24. Okay, and I'm just going to use my calculator on this. I'm not going to graph it or anything. I like to graph on these problems at the end because I want you to understand the methodology and use the graphing to check. So basically I've just got this. 2 times -3, nope, 2 times -2 to the third, and then minus 3 times -2 to the second. Now you can do some of this in your head if you want to. And then we're going to have subtract 12 times -2. Okay, and then plus 24. Just be sure you put things in carefully, double check, make sure you got everything in there right. So that looks good. And then we'll record what that is. So that value is 20. Wow. Emergency. Hold on. Okay, the world didn't come to an end. So I think we're okay. Every now and then I get these text message alerts if there's a police report in my neighborhood or something, like somebody, a mysterious person's been walking around, or there's been a stolen vehicle or that kind of thing. So my doors are locked, so I think we're safe. All right. If anybody, an intruder comes in and sees me teaching calculus, they're going to run away. Anyway, haha. Okay, so let's go to the next thing here. We do 2 times 4 to the third. Okay, like that. And then we'll do subtract 3 times 4 to the second. And minus 12 times 4. And plus 24. Okay, and put that in, so that gives 56, so that's a bigger number like that. Okay, now what I need to do is we also have to evaluate the critical numbers, because the absolute max and min could be at the critical numbers, so we're going to do g of -1. So we do 2 times -1 to the third, minus 3 times -1 to the second, minus 12 times -1, plus 24. And then we need to do g of 2. So g of 2 would be 2 times 2 to the third, minus 3 times 2 to the second, minus 12 times 2, and then plus 24. Okay, so I'm just going to crunch those on my calculator, and then we should be able to get our answer. Okay, so I just do 2 times 2 to the third. Okay, and then minus 3 times 2 to the second. You can do some of this you can do in your head. I'm just trying to put exactly in what I wrote down. Okay, saves a little bit of time if you just do simple things in your head. Okay, so that would be evaluated as 4. Okay, then we'll do the last one. We'll do 2, and I'll show you what I'm talking about. 2 to the third's 8. So I just kind of go like this. Minus 3 times 2 to the second's 4, and then minus 24, and then plus 24. Okay, whatever you want to do. Okay, so that also gave a 4. Okay, so what we have now is, once we get these things crunched out, we just need to identify the biggest one. So the absolute, let's do the min first. The absolute min would be the lowest numbers. These are a tie, so these would be your absolute min. So we would conclude that we have 2 points. There's 2 absolute mins. You would have -1, 4, and you would also have the point +2, 4. Those would be 2 places where those are the lowest y values you ever hit. Okay. Then we want to do the absolute max. Okay. The biggest one looks to be that one, 56. Okay. So here's your max. So that would occur at a point 4, 56. Okay, so we've got the answer of the problem. Now what I would recommend you do, I mean, you're allowed to use a calculator and use technology on your test. By all means, this doesn't take more than a minute. You just need to graph this function, 2x to the third minus 3x to the second, and then minus 12x, and finally plus 24. Window, you could do a standard window to start with and just see if you see this. Actually, I made a mistake. You need to graph just from -2 to 4. So we're just going to do the interval from -2 to 4 only, because that's all we care about. And then we might need to expand these numbers. See, our max is at 56. So for that reason, I'm kind of inclined to go -60 to 60. That way that 56 will show up, and then maybe scale that by 10. Okay, so that's a good way to do that. And what this will do is this will verify the answer for you. Okay, so let's see. We got minimums at -1 and 2. So if I trace at -1, did I make some sort of mistake there? Oh, it's not negative. -1, 4. Oh crap, I did make some kind of mistake here. It looks like if I trace it 2, that looks like the absolute min of there. The absolute max 456, if I trace it 4, you can tell that's the absolute max there, but maybe I made a mistake on this -2. So I'm going to, or this -1. If I trace it -1, that should have given me 31. Okay, so did I plug that in wrong or something? I must have. Okay, I must have done that. So it looks like, and this is the benefit. I could lie and said I did this on purpose to show you how you catch mistakes, but I made a mistake. So that at -1, you have 31. Okay, so it looks like what happens then is you have one min, and that min is going to be at 2, 4. So that's the absolute min, 2, 4. We verified that on the calculator. Again, by tracing it 2, you can visually tell that's the min. And then tracing it 4, you can visually tell that's the absolute max. So I did make a mistake, okay? All right, but that's why you check. Okay, so good lesson. Okay, I'll pause for a bit. Okay, check, check, 1, 2, check, 1, 2. Okay, so the next thing that I'm going to look at is going to be the concavity. Okay, so what I've done is I've given a function. All right, and this time what we're going to do is just analyze the concavity. All right, so to begin with, concavity, you have to analyze the second derivative. So we're going to start by doing the first derivative. So f prime of x on this is going to be 4x to the third minus 36x. Okay, and we don't want to do anything with setting that to 0 because we're moving straight onto the concavity. So if you do your second derivative now, you're going to get 12x to the second minus 36. Okay, then that's what we're going to set equal to 0. Okay, so what I'm going to do now is we're going to set the second derivative equal to 0. Okay, so we can do this. We can solve this. There's a couple ways you could do this. One thing you could do is you could factor a 12 out. And if you factor a 12 out, you would have x to the third minus 3 is equal to 0. All right, and really what matters is the x squared minus 3. So I'm going to divide by 12. You can always divide an equation by a constant. And what I'm going to have here is I'm going to have x to the second minus 3 is equal to 0. So I'm going to add 3 to both sides. That'll give x squared equals 3. I'll take the square root of both sides. And be sure that you understand here that you're getting two answers when you do the square root. So you have two places where it looks like the second derivative is equal to 0. Okay? So that's how you want to start that. Now the third thing you want to do with concavity, just like if you're doing increasing, decreasing, you want to do a sign chart. Okay? So what we're going to do here is we're going to look at negative square root of 3. And we're also going to look at positive square root of 3. All right. Now, the second derivative, you can plug it in either to 12x squared minus 36, or you can plug it into x squared minus 3. It doesn't really make any difference of that. If you divide by 12, that isn't going to affect the signs that you're going to have on here. Okay. So let's go ahead and I'm going to plug it into the 12x minus 36. Okay, so let's take anything, negative square root of 3 is about negative 1.7. Okay, and then what I'll do is we'll just put in something like maybe negative 2. Okay, and we'll plug it into that second derivative. So that's 12 times negative 2 to the second minus 36. That's 12 times 4 minus 36. That's a positive result. That means the function is concave up. Okay, pick a test point between negative root 3 and 3. 0 is a good obvious choice. So we'd have 12 times 0 to the second minus 36. Okay, what matters is that's a negative result. That means you are concave down. Okay, and then lastly, pick a test point bigger than square root of 3. Square root of 3 is about 1.7. If you don't know that, just get your calculator. Put a 2 in. So now we'll have 12 times 2 squared minus 36. So that's 12 times 4 minus 36. That's a positive number. So we're back to concave up. Okay? So it's usually best to just plug right into the second derivative. You don't have to worry about, this one doesn't factor, so it's just as well to plug in there. And a couple of things I want to remind you of is when you're dealing with the second derivative, you have the happy guy, you're concave up. You have the sad guy, you're concave down. All right, so now we're ready to answer our questions on this then. So concave up would be these two locations here. Okay, so I'm going to write that down in an interval. So that's going to be from negative infinity until negative square root of 3, then union square root of 3, and then to infinity, like that. Okay, all right, and then concave down is going to be between these two values. Okay, so that will end up just being negative square root of 3, comma square root of 3. That should be the answer there. Okay, now what a point of inflection is a point of inflection has to be a point on the graph where the concavity changed. And basically the concavity changed in two locations. Okay, the concavity changed at that place and that place. So our points of inflection are going to be at negative square root of 3, we'll figure out the y value here in a minute, and square root of 3, and then we'll figure out the y value. Okay, now what you want to do to figure out the y value, you need to go back to the original function. So we need to evaluate the function at negative square root of 3. So we're going to do negative square root of 3 to the fourth minus 18 times negative square root of 3 to the second. Now I'm going to work this out without a calculator. You can certainly do it as a calculator, but this is, if you take a negative number and multiply it out 4 times, you get a positive. And then this would just be the square root of 3 to the fourth, which is 81. This would be 18. Again, you're squaring a negative, so this is a positive. So you end up just getting the square root of 3 squared. Okay, so what will happen on this then is, if you want to do it this way, you can. The square root of a value to a power is always just half of that. So this would be 3 to the second. And then the 18, if we do the square root of 3 to the second, that's 3. Okay, so you end up getting 9 minus, and let's see, that's 54. Okay, and I'll show you how we can check on our calculator and everything. So that would be negative 45. So it looks like the y value of that point of inflection is going to be negative 45. Okay? Now, you can tell that it's good to know how to do stuff like this algebraically by hand, but, I'm going to go back and I'm going to put in what I have here. You could put this in on your calculator like this. You could go parentheses negative square root of 3, okay, like that, and then raised to the 4th power. That's going to work that out for you. And then you could put in subtract 18, then parentheses negative square root of 3. Whoops. So I put in square. Oh, come on. Getting all messed up there. There we go. Okay, negative square root of 3. Again, close parentheses to the 2nd power. So you can put that in and you got negative 45. Now what's going to happen if we do f of square root of 3? You're going to get the same answer. I mean, it isn't going to make any difference on that. So you're going to get, you're still going to get the negative 45. Okay, so that would be your 2 points of inflection then. Okay, now the other way you can get that negative 45 if you want to is like this. We might as well check the answer to the problem, see. So if I just graph this, I'm going to clear off the graph I had from a previous problem. And if I do this, let's see, I'll have x to the 4th, and then subtract 18 x to the 2nd, okay, and I'll just do whatever window I had on the last problem, okay, and let's see, well, I probably need to maybe expand this out a little bit here. Let's just start with a standard window, zoom 6, okay, and probably the only thing I need to do on this is maybe expand the y's a little bit, so let's go maybe like negative 100 to 100 by a scale of 10, and just see if that's a pretty good viewing window. Okay, so that looks good. So now if you look at this, see we're concave up, then concave down and concave up. So that's matching what the sign chart said. So if you trace at negative square root of 3, okay, which is where we found a point of inflection, so that's negative 45. That's where this graph changes from concave up to concave down. So that verifies that's right. And then you would trace at positive, whoops, not like that, trace at positive square root of 3, and then that would be at the other point of inflection. So see, that looks perfectly the way it's supposed to look. So I want to encourage people to learn how to use technology to make sense out of this stuff. So basically, there's your concave up there and there. And then your concave down is right here. Okay, and then that should verify the answer to the problem. Your points of inflection are those 2 points right there. Okay. Okay, so the next thing that I'm going to look at on here is this problem 6. Okay, this is where you're given conditions and you're trying to make a possible graph. So what I usually recommend you do on this is, let's just number these things and write down what they are. This first statement says f of 0 equals 2. That just means there's a point 0, 2 on the graph. F of 1 equals 0 means that if x is 1, y is 0, so that's a point on the graph. And if f of 2 is equal to negative 2, that means 2, negative 2 is on the graph. So what I'm going to do is I'm just going to plot those points then. So I've got 0, 2, that needs to be on your graph, 1, 0, and 2, negative 2. Okay, so that takes care of that. Those things have to be on your graph. Okay, the next thing is talking about the derivative. The derivative is equal to 0. If the derivative is equal to 0, then this just means you have a horizontal tangent line. So if x is equal to 0, and x is 2, since the derivatives are equal to 0, this just means the tangent line's horizontal. So what I'm going to do is just write a note to myself. If x is 0, this point right here is going to have a horizontal tangent line. So I'm just going to mark that in there. Same thing with x equals 2. I have a horizontal tangent line. So I'd be looking at those two aspects of your graph. Okay, number 3 is this statement, and first of all, what this is saying, kind of break this up into two parts. Okay, the first derivative is positive. If the first derivative is positive, greater than 0, that means this function is going to increase on negative infinity to 0 and to infinity. So that's what that means. Okay, so that's statement number 3. All right, so if you were going to do this, just kind of think, okay, from negative infinity to 0, so out from here to here, the function's going to increase. So this function's going to go up and kind of do something like that for now. And then from 2 to infinity, we're also going to increase. Okay, I'm not going to draw anything on the graph. I'm just writing a note to myself. Okay, the fourth statement basically is saying this. The second derivative is negative, or I'm sorry, the first derivative is negative. That means the function is decreasing on the interval 0 to 2. So that's what that statement says. So I'm just going to kind of make a note to myself. Okay, I'm increasing from here to here, from here to here, and then I'm going to decrease from here to here. Okay, I'm not going to draw a graph. I'm just kind of writing notes to myself. Okay. Then we move on to number 5. Okay, the second derivative is 0. That means that you might have a point of inflection, okay, at x equals 1. Okay, if x is equal to 1, the second derivative is 0. There's a strong possibility that that's a point of inflection. Okay, so we already have that point here, so I'm just going to kind of write a note to myself, inflection point when x is 1. Okay, number 6, okay, if the second derivative is positive, that means you're concave up. Okay, so that means we are concave up on the interval 1 to infinity. Okay, so I'm going to say this kind of green part right here, I'm just kind of making notes to myself, so that's concave up. Okay. And then number 7 is saying that the second derivative is negative. So remember what that means is if the second derivative is negative, then you're concave down. So statement 7 is just going to say you're concave down from negative infinity to positive 1. Okay, so again, I'm just going to kind of write a note to myself right here. We are concave down there. Okay, now what we're ready to do is we're ready to just sketch the graph down. Okay, so we're concave up here. That means this graph's going to have to go like this. It's going to reach a low point, and it's going to go up. You're concave up. Okay, concave down is going to be like this. Okay, you're going to be going kind of like that, like that. That's a good possible graph on there. It has every characteristic that I stated. It doesn't have to look precisely that way, but you do have to have, you're going to have a min there, you're going to have a max there, you're going to have a point of inflection there, and then you've got everything else. Notice that it's increasing from negative infinity to 0, it's decreasing from 0 to 2, and then increasing. So that has every characteristic, and one thing that's helpful is to just write notes to yourself the way I did there. It's hard to just put this all together in your head. So I highly recommend you approach the problem this way. Okay, now the next thing I'm going to look at is L'Hopital's rule. And we'll go ahead and run through some of these problems. So L'Hopital's rule is you're back to doing limits again. And the thing on this is the first thing that you always want to do is see if you have the correct form. So really all you do is just plug in. This is a limit as x goes to 0. So you'd have e to the 4 times 0 minus 1 times 4 times 0 all over 0 to the second. Okay, if you work that out, that's e to the 0, so that's 1 minus 1 minus 0 over 0. So that is a 0 over 0 form. So you always want to make sure that it's either 0 over 0 or infinity over infinity. So since it is 0 over 0, we can go ahead and do L'Hopital's rule. This will be the second part of the problem. And remember, that means we're going to do the limit still as x goes to 0, but you need to do the derivative of the top, okay, which you can do in your head. The derivative of e to the 4x is e to the 4x times the derivative of the exponent. That's a chain rule. The derivative of 1 is 0. The derivative of negative 4x is negative 4. Okay, and then we want to go to the bottom. You want to do the derivative of x squared. So the derivative of x squared is going to be 2x. Okay, now let's just kind of clean this up and see what we have now. So we still have the limit. X goes to 0. Now it looks like we have 4 times e to the 4x minus 4 over 2x. Now, if you plugged the 0 in now, you would still have 0 over 0. So what would happen on this now is when you plug in, you would have 4 times e to the 4 times 0 minus 4 over 2 times 0. That would be 4e to the 0 minus 4 over 0. That's 4 times 1 minus 4 over 0. So again, that's 0 over 0. So it's going to have that form again. So what we need to do then is from here, we need to do L'Hopital's rule a second time. So I'm going to just call that LH2. So since we have 0, 0 a second time, then we do L'Hopital's rule again. So we're going to do the limit. X goes to 0. And we're going to do the derivative of this numerator. Okay, so that's a chain rule. The derivative of 4e to the 4x. 4 is a constant. Write it down. We'd have itself, e to the 4x, times the derivative of the exponent. And then the derivative of the 4 is 0. Okay, so you got to get your derivatives correct, of course. The derivative of 2x is 2. And we're just going to reevaluate the limit now. So what we actually have is we have the limit as x goes to 0 of 16 e to the 4x all over 2. And if you want to reduce that down, you would get this. So we would have the limit x goes to 0 of 8 e to the 4x. Now plug in. So now we get 8 e to the 4 times 0. So that is 8. Let me write that just a little bit clearer here. Okay, so we have this. We have 4 times 0, so that's going to be 8 e to the 0. That's 8 times 1, so the answer is 8. That problem has a lot of work on it because you had to do L'Hopital's rule twice. Okay. Now, what you can do on these problems, if you want to, I mean, you don't have to, but you can graph what you're doing there. I'm going to block some of this off. I'm going to show you what I put in my calculator. So what I'm going to do is you would put this in your calculator like this. So you would have e to the 4x. Okay, get out of the exponent. Then we'll have minus 1 and then minus 4x. Close parentheses, divide by x to the second. So I'm just going to graph that in a standard window, and it's probably good enough. Okay, so zoom 6. Okay. What we just found is the limit is equal to 8. So let me show you what happens. If I trace at 0 on this, well, I'm undefined. This function's undefined at 0 because you have a 0 denominator. Well, so if you pick a number close to 0 and trace, I'm going to trace like instead of 0, I'll put 0.0001. We should be close to 8. And we are. See, that's 8.00107 like that. So if you look at that, this pretty well verifies graphically it's right. Now, I wouldn't give you credit if you just graphed it on your calculator. You have to go through the steps of L'Hopital's rule. Okay? But you want to close off all your problems that way if you can. Okay? So that verifies that we're right. Okay, this next one, step 1 again, we're going to look at the form. So if you plug in infinity, we're going to have infinity to the third over ln of infinity. Infinity to the third just gets infinitely big, so does ln of infinity. Okay, what happens is ln just gets bigger and bigger infinitely. So you have the right form, so that means now we're ready to go to step 2 where we're going to use L'Hopital's rule. Okay, so what I usually tell students to do is put an equal sign, put LH for L'Hopital's rule. we're going to be doing the limit as x goes to infinity. We'll do the derivative of the numerator, and the derivative of x to the third is 3x squared. Okay, then we'll do the derivative of the denominator, which is 1 over x. Okay, now we need to algebraically simplify that, and don't let the complex fraction bother you. This is just saying 3x squared is being divided by 1 over x, so therefore it's 3x to the second times x over 1. You're multiplying by the reciprocal, so that's 3x to the third. All right, now what we're going to do is try the limit now. So we'd have the limit x goes to infinity of 3x to the third. Well, if you plug in infinity now, this just gives you 3 times infinity to the third, which is infinitely big. So that means that limit is going to go to infinity. Okay. And again, what you could do on this, okay, you've got the answer of infinity. You might as well find out if you're right. So what you would do is just graph this function I gave you. So the function is x to the third, okay, and then divide by ln of x. And again, I'll just do this in a standard window and just see kind of what this graph looks like. So here's zoom 6. Okay, we probably want to maybe expand this out a little bit. You can do this zoom out if you want to do like this. Zoom out is kind of a quick thing you can do. Sometimes the window's funny when you do zoom out. But what's going to happen on this is this. You could even look at your table of values. Is what happens is these numbers just get bigger and bigger and bigger forever. It's never going to slow down, okay? So you can even look at the problem that way if you want to, okay? All right, so that looks like a good answer. Okay, the next one, we'll just kind of work out the same way. Step 1 is to look at the form. Okay, if you plug in a 1, we would have 2 times 1 to the third minus 3 times 1 to the second plus 1. The denominator would be 1 to the third minus 3 times 1 plus 2. So that's 2 times 1 minus 3 plus 1 over 1 minus 3 plus 2. So that looks like 0 over 0. Okay, so you have to do that first because you can't use L'Hopital's rule unless it's 0 over 0 or infinity over infinity for this class. Okay, all right, now that means let's do L'Hopital's rule. Okay, so we would have the limit x goes to 1. The derivative of the numerator is a pretty easy one to do, so we'll do that. Okay, so that's going to be 6x squared minus 6x. Do the derivative of the denominator. Okay, and that will be 3x squared minus 3, like that. And you could, you could factor out a 6 and factor out 3 if you wanted to, but you don't have to. Might as well just check it again and see if we have to do L'Hopital again. So we'll plug in a 1. So we have 6 times 1 to the second minus 6 times 1. 3 times 1 to the second minus 3. That's 6 minus 6 over 3 minus 3. So again, we got this 0 over 0 form. So that just means we're going to do L'Hopital number 2. So we're going to do the limit. X goes to 1. And again, we're going to do the derivative of the numerator, which is 12x minus 6. We'll do the derivative of the denominator, which is just 6x, like that. Okay, and then we can try again and see what happens. So now if we plug in, we're going to have 12 times 1 minus 6 over 6 times 1. So we end up getting 6 over 6. So we end up getting 1. And I think, no. I think I made a mistake on there somewhere. Hold on. No, I'm okay. For some reason, I was thinking that this limit was going to infinity, and it's not. So I was kind of seeing this horizontal asymptote in here of 2, but this limit's not going to infinity. So looks like I'm okay on that. Okay, and again, I'll go ahead and let's just do a quick checkaroo here. Okay, these are the kind of things you can do at the end of the test, and just kind of catch some mistakes if you do that. Then it takes a little time. It takes about a minute to put all this stuff in. So we have 2x to the third and minus 3x squared. And then plus 1. And divide by, let's see, then we have x to the third. And then minus 3x. And plus 2. Okay, again, I'm just going to do standard window, zoom 6. And we're going to look at the limit as x goes to 1. So again, if I trace at 1, we're undefined. Okay, there's actually a bubble in that graph there. So instead, we will trace at 1.0001, something close to 1. And notice that gives us close to our answer, which is 1. So that graph right there verifies that. Okay. Okay, I'm going to do problem 8, and then I'm going to do this video in 2 steps, so usually a little bit better to do it that way. So let's go ahead and move down here, do this, then I'll close this off, post the video, then I'll do the second part. Okay, this one you're looking for, you have a baseball manufacturer planning to expand the workforce. It estimates number of baseball caps produced by hiring X workers. So X is the number of workers, is given by this function, and we're going to graph this probably from 0 to 18. Find the diminishing returns. Okay, so first of all, before we even do the calculus, let's just go ahead and go to part B and let's graph this. Now you're going to graph this with your graphing calculator. And there's a couple of things that are real important that I want to mention about graphing. One of the things that I see a lot from students, and it's really bad, yeah, I might as well just be blunt with you. Students a lot of times don't label anything on their graph. I mean, they don't put a scale. You need to know what I mean by scaling the axis. You got to have an accurate graph. You're using technology to do a graph, so there's absolutely no reason why you shouldn't get a graph perfectly right. So I'm going to put that in. Now the window, I'm telling you I want x to go from 0 to 18. So that will be your x window right there. And then you can scale that by 1 or 2 or whatever you want to. Okay, that's totally up to you. I'm going to go maybe by 2. Okay. Now the y value, now if you need to figure out the y value, look at your table of values. Okay, so just go like second graph. And just kind of go back and look between 0 and 18 and get a sense for how big these numbers are. Okay, when x is 0, you're at 0. And then when we make it all the way up to 18, these numbers are just increasing. You're all the way up into almost 9,000. Okay, so to me, a good way to do this then would probably go like this. Go 0 to 9,000. And then scale that maybe like by 1,000 or something, okay? Or 3,000 or whatever you want to do. So that would be a really good viewing window to use like that. I guess that's what I have there. So I figured out the same thing. So now we'll graph it and do this. Now, when you're doing a graph, there's this tendency for students to do this. That's their answer. If you do that, you wouldn't get any credit for the problem. That is absolutely meaningless. Okay, the first thing that you got to do, when I say scale the axis, that's just like kind of showing your window. So we're going all the way to 18. So we're going to go 2, 4, 6, 8, 10, 12, 14, 16, 18. And then you at least do some of these, okay? You don't have to put every single thing on there, but you could even scale it by 3s if you want to. That is your decision. But this is what I mean by scaling the axis, and you must write this scale on your paper. Otherwise, it's meaningless. Okay, when we did the y's, okay, we're going from 0 to 9,000. Okay, so you need to figure out how you're going to do this. I'm going to make every 2 1. So that'll be 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000. Okay, like that. And you need to label what everything means, okay? X is X new workers. Okay, that's what that is. Tell me what it means, okay? You're giving a graph that has meaning to it. And then what this says, it says the number of baseball caps produced. So this axis here is number of baseball caps. If I put number of caps, that's good enough, okay? Then you want to put your scale. Now you can use K. These are going by 1,000, so you could go 1K, 2K, 3K, 4K, 5, 6, 7, 8, 9K like that. But you have to label something. That's what I mean by scaling the axis. That must be there, okay? And the other thing is, then students a lot of times just do this nonsense again. That's meaningless, okay? Usually what you want to do is get a few points, okay? So let's on this one just kind of get pick some points. Trace. You can go trace at 0. You got a point 0, 0. Okay, and I'm going to label this in red, so that's a point. Just label it. You probably want to label the last point, so if you trace at 18, okay, then that's go over to 18, and that's up about, and you don't have to be perfect. Here's 9,000, so it's somewhere in there, but go ahead and label it. 18, 8, 7, 4, 8, like that. Now the third point is probably the best one to use on here is the point of diminishing return. So we'll come back to our graph here in a minute. Okay, so now when we do the point of diminishing returns, what we're going to have is we want to go ahead and start by doing the first derivative, which is bring that power rule. So that would be 0.25 times 4 is 1, so that's negative 1, x to the third plus 18x squared. Go to your second derivative, okay, because you're looking at a point of inflection is what this is. The second derivative is negative 3x squared plus 36x. So when you're doing a point of inflection, you need to set the second derivative equal to 0, and then we'll do a sign chart to see if the concavity changes. Okay, so this one can be solved by factoring. What I'm going to do is factor out a negative 3x. So we can take a 3 goes into 36. You have an x in both locations. So this would just be x here. And then you multiply 3 by 12 to get that, but it's a positive, so you would have to write that like that. Okay, now you got to get things factored correctly, and it's always important to check by multiplying out. So what you get is you get negative 3x equals 0. That would give x equals 0. That's not what we're looking for. That's just the beginning, so that's not the one we want. Then we do x minus 12 equals 0, so we get x equals 12. Okay? Now what we can do on this one, and on this kind of a problem right here, since we're doing this graphically, let's see if that looks like a point of inflection. So let's just trace at 12. That's a technology problem right there, and then that would be the next best point to plot. So if we go over 12 and then up about, let's see, this is 2, 3, 4, 5K. So it looks like it would be kind of up in here. Doesn't have to be perfect, just ballpark. So 12, 5, 1, 8, 4 like that. All right, and then the rest of it's sketched. Now you can kind of see that this thing is concave up. And then from here, the concavity changes to concave down. Okay, now that right there is a really good accurate graph. It's not perfect, but it's got at least 3 points on that. Okay, so that's what I'd be looking for. And then this point of diminishing returns is 12, 5,184. That's okay. You don't really have to do a sign chart on this since you're doing this graphically. But if you did, a sign chart would go like this. You would have 0, you would have 12. If you plugged into the second derivative, which is negative 36x squared plus 36x, if you did a test point, like if you plugged in a 1 into this and did negative 3 times 1 to the second plus 36 times 1, you would get a positive. You're concave up. If you plug 13 in, you would do negative 3 times 13 squared plus 36 times 13. If you did that and took the time to crunch that out, you would have a negative, so you'd be concave down. Okay? All right, so that's it. All right, that's the way the graphs need to be, and you need to take pride in your graphs. They got to look right. Like you're a business person and you're making a presentation. These are the number of new workers. That's the number of baseball caps, and this is the point of diminishing returns, which means that after this point, as we add more workers, the number of caps is going to continue to increase, but at a slower rate. Okay, so this right here is your point of diminishing returns. Okay, so that will be the end of this part of the video. All right, thanks for watching.